Sadi Carnot and the Power of Fire, the 1824 edition, Part 2, is an episode of the Degrees of Freedom Project, videos on chemical and thermal principles. Definitions and additional details can be found in the webpage link in the description. These two videos, Sadi Carnot and the Power of Fire, the 1824 edition, Part 1 and Part 2, present two examples of how you might actually implement a Carnot cycle in the physical world. Part 1 presented the air standard Carnot cycle, and Part 2 presents the steam Carnot cycle. We will use these two examples as the basis for all of the power and refrigeration cycles we will study. We will now create a Carnot cycle using water, steam, as the working fluid. We will begin with a diagram of the 4 steps in the cycle. States A, B, C, and D correspond to the same states on the air standard Carnot cycle. The 4 steps correspond to a pump, a boiler, a turbine, and a condenser. Here is the corresponding labeled TS diagram for the cycle. The dome-shaped curve is the phase boundary for the two-phase region in the water-steam phase diagram. We begin with a mixture of liquid water and steam with some quality at point A. We will then pump and compress it with an isentropic pump to point B, which will be right on the boundary line of the two-phase region as saturated water. We will then have our isothermal heat addition in the boiler, where we will convert the saturated liquid water into saturated steam. Oh, so that's how you have an isothermal reservoir. You have a phase change which occurs at a constant temperature. That takes us to point C. Now we will expand the fully saturated steam through an isentropic turbine and get to point D, where we have again a mixture of steam and liquid water at some quality higher than at point A. Finally, we will condense quite a bit of the steam to get us back to point A again. Let's analyze each of the subsystems, the boiler, the turbine, the condenser, and the pump in turn. This is going to be an exercise in how well you can use the steam table. We'll start with the boiler. The first law for the boiler is that delta H dot equals Q dot equals M dot delta H hat. We now look at the steam tables for the enthalpy of saturated liquid and saturated vapor at 200 degrees Celsius. The enthalpy of saturated steam is 2792.1, and the enthalpy of saturated liquid is 852.33. And so that gives us our delta H for the process. Next, we will look at the turbine, and the first law says that delta H dot equals negative W dot shaft because it's adiabatic. Delta H dot equals M dot delta H hat, and we don't know what H hat is at point D. To find it, we'll need the second law. The second law still states that for an isentropic turbine, delta S equals 0 equals M dot delta S hat. So we know that the entropy at point D is going to be the same as entropy at point C, which we already know. Point D is in the two-phase region at 200 degrees Celsius. So S hat C is going to be S hat of the vapor at 200 degrees Celsius from the steam table, which is 6.4303. Looking in the steam table at 100 degrees Celsius, we get that S hat of liquid is 1.307 and S hat of the vapor is 7.3541. So now we need to use the mixture-specific entropy to calculate the quality. Just as a reminder, the mole or mass fraction of steam is the quality, which is the mass of vapor over the total mass. Then the specific entropy of the mixture is S hat of the mixture equals X S hat V plus 1 minus X times S hat L. In our case, 6.4303 equals X times 7.3541 plus 1 minus X times 1.307, or X equals 6.4303 minus 1.3070 divided by 7.3541 minus 1.307 equals 0.8472. So we have the quality now at point D. With the quality, we can calculate the enthalpy at point D from the steam table as X H hat V plus 1 minus X H hat L. The specific enthalpy at point D is 230.9. By a similar process, assuming that our pump is also isentropic and knowing the entropy at point B, we can calculate the quality at point A as being 0.1693. And that lets us calculate that the enthalpy at point A is 801. Finally, we can calculate the efficiency of the cycle as either being the net work by combining the change in enthalpy for the turbine and for the pump, or we can calculate Q hot minus Q cold, and plugging in either of those with all the enthalpy values that we've calculated, we get that the Carnot efficiency is 0.2113. Let's compare the efficiency that we got by calculating the full cycle with what we would get from the Carnot efficiency, where eta equals 1 minus T cold over T hot, which is 1 minus 373.15 divided by 473.15, which equals 0.2113. So, to as many significant digits as we have in our enthalpies and entropies, the efficiencies come out to be the same. The net work for the process turns out to be negative 410 kilojoules per kilogram, and Q hot turns out to be 1939.8 kilojoules per kilogram, and Q cold equals minus 1529.8 kilojoules per kilogram. We have now demonstrated two different Carnot engines, one where each step was a closed system and air was the working fluid, and one where each step was an open, steady-state system with water as the working fluid. As mentioned, we will use the first one as the basis for air standard power cycles. The second one will be used as the basis of the Rankine cycle, which is the basis for all of the big steam-generating power plants, whether they are powered by coal, by natural gas, or by nuclear energy. So what are the engineering problems with the steam Carnot cycle? We will let you ponder those for a while, and we will move on to other things. So now another big question. What happens if we run a Carnot engine backwards? In this case, we're going to extract heat from our cold reservoir. We're going to pull out Q cold and put it into our engine. We will then put in some work, W, into our Carnot engine. and then we will reject the combination of Q cold and W as Q hot into our hot reservoir. So let's work through the equations. As before, absolute value of W over absolute value of Q hot equals 1 minus T cold over T hot. Notice that we've changed the directions and therefore the signs of everything when not using absolute values. We will rewrite our efficiency expression as the absolute value of the work over the absolute value of the work plus the absolute value of Q cold, and rearrange our other expression to get T hot minus T cold over T hot. For our backwards heat engine, we're actually interested in Q cold for some reason, and so we will solve that expression for Q cold, and we will get Q cold over W is equal to T cold divided by T hot minus T cold. Q cold over W we will now call omega, which is our symbol for the coefficient of performance. What in the world is a coefficient of performance? Well, what do we call a device that removes heat at low temperatures and rejects it at a high temperature? Most of the time we refer to that as a refrigerator. Occasionally we refer to it as a heat pump. So the coefficient of performance is what we want, which for a refrigerator is the cooling to keep our food cold divided by what we have to pay for, which is our work. So this coefficient of performance is a measure of the minimum amount of work that we have to put in order to get a certain amount of cooling in our refrigerator. So now you know how to run both the Carnot heat engine to generate work and a Carnot refrigerator to generate cold. The videos Boil, Expand, Condense, Repeat, the Rankine cycle in action, Part 1 and Part 2 explains the Rankine cycle, which is based on the Steam Carnot cycle. Finally, the video Revenge of the Fridge, Vapor Compression, Strikes Back, examines refrigeration cycles. The takeaways from this video are: 1. The Carnot cycle consists of an isentropic temperature rise, an isothermal heat addition, an isothermal temperature drop, and an isothermal heat removal. 2. The Steam Carnot cycle implements the 4 steps with an isentropic compressor, an isothermal boiler, an isentropic turbine, and an isothermal condenser. 3. A Carnot engine running in reverse is a refrigerator. Thanks for watching. This video is brought to you by the DOFPro team.